So our next speaker is Bryce from UC Berkeley, and he will tell us about the teleportation via operator spreading in the Traversable Wormhole protocol. Please.
Okay, well, thank you everyone for coming, waking up early, joining the call. My name is Bryce Kobrin, and yeah, the focus of our talk today will be on this Traversable Wormhole protocol and looking at that from the perspective of operator growth. This work was done in collaboration with another grad student at Berkeley, Tommy Schuster, and our advisor, Norman Yao. So the broad context, whoops. That works. The broad context for this talk is thinking about ways of adopting tools that are developed in the context of quantum gravity and using these more broadly to study the dynamics of other more generic many-body quantum systems. And I think the most familiar example of this is the story of out-of-time ordered correlators. So these were a tool that I think were developed, or at least first fully understood, appreciated in the high energy context as a way of probing black hole dynamics. In particular, they correspond to probing a high energy scattering event near a black hole horizon. And looking at it in this way gave some expectation about the form of these operators, the fact that they grow exponentially, like a classical a chaos effect, and also taught us something about the rate of growth, and that is bounded by a universal temperature-dependent factor. And so what happened was, then these correlators were reported over and looked at from a more microscopic perspective, or in other words, as using the boundary degrees of freedom. And here, the intuition was that they probed something about operator growth. So in particular, if you start off with a very initially very local operator, and evolve it later in time, what it does is it probes the overlap with another operator and tells you how fast it has grown. So once we in the condensed matter atomic physics community learned about these correlators, we really took them and studied all sorts of different systems with them. And it's been a very, very fruitful activity. So there's been a number of very, very nice calculations of OTOCs in different types of systems that don't necessarily have a close connection to gravity, from condensed matter disordered metals, random circuits, localized systems. And what was found is that there's a whole spectrum of different behaviors of these correlators, and that using these correlators helps to understand the dynamics of these systems. There's also been a lot of work using these correlators outside of regimes of analytic control as a numerical tool. So I personally have worked on this quite a bit in the recent past. And here things get a little tricky because in finite systems at early times, there are a number of competing dynamics that are occurring. One must be very careful in using these correlators and scaling both the numerics and also understanding the different corrections that happen. And here, again, the lessons that we learned is looking towards gravity to understand some of these effects is very helpful for us to build these tools and understand how to use them properly. There's also been a push on the experimental front to start measuring these correlators in the lab. Many nice proposals for doing that, and some early demonstrations on different experimental platforms. Here, the experimentalists face their own set of challenges. In this case, these correlators, it's known that they are susceptible to the noise in the system. So if you have a system, well, it's expected that these correlators decay under some scrambling dynamics, but they can also decay due to simpler noise in your system. And decoupling these two effects is a challenge for the experimentalists. So the focus of this talk is in identifying and starting to understand a new tool that's been adopted from high energy that gives a similar that's another probe for scrambling dynamics. And the context for this tool is really twofold. One of them is asking questions about the black hole information paradox. going back to thought experiments of Hayden Preskel, more recent work by Yoshida Kitaev, and also asking about doing dynamical questions about these traversable wormholes that were first discovered a few years ago, and whose details have been worked out quite thoroughly. So in the microscopic side, what these two pictures in gravity correspond to is a teleportation circuit. And so this will be the focus of our talk. And here's the circuit, which we will go into more detail. But the key message or the key feature of this circuit is that the teleportation depends on having a scrambling unitary, or even the properties of that unitary. And so using this circuit is a way of probing those properties. One of the immediate advantages of this circuit, which was realized by Norman and Benny Yoshida, is that it's more robust against the presence of experimental noise. So whereas before with the O-talks, we saw that both noise or scrambling could lead to the decay of these correlators, with teleportation, noise itself cannot lead to teleportation. And so a sign of or teleportation, successful teleportation, is an indicator of intrinsic coherent scrambling dynamics, and you can formally relate the two quantities. And so this has led to a couple of very beautiful experiments recently by the Monroe group. This data is actually taken from their experiment, and a similar experiment was recently wrapped up in the Siddiqui group on a different platform of superconducting qubits.
Bryce?
And so yes?
I had a question. To what degree does the statement that you just made by Yao and Yoshida imply that Hayden Preskel itself is robust to noise?
That Hayden Preskel, so the basic statement is very simple. It's that in order for teleportation to work, you need two things. You need scrambling. So this whole circuit will depend on having scrambling. And you also need a low level of noise. And so you can relate so if you have a strong amount of noise, then you won't have teleportation. If you have a strong amount of noise, though, your O-talk will decay. And so seeing teleportation is an indicator that you have low noise and you have scrambling dynamics, and you can relate those two. So this formula is taken from their paper. You can do some formal bounds on those two quantities. But generally, it's if you see an experiment, it's a good signal. You can't have any false positive, let's say, the way you can with O-talks. Is that
I guess
sufficient? Yep.
I guess, okay, that's interesting, but it's not quite what I was asking. I guess my question is, what is the implicative relationship between the teleportation protocol being successful and Hayden Preskel working? Because I would naively have thought that if I introduce some amount of noise into Hayden Preskel, it might prevent me from reconstructing.
That's correct. That's what I'm saying. Yes. But I mean, what it means is that you can verify if you had signals. So if Hayden Preskel was successful, it's verifying that you had scrambling coherent dynamics. Because if you had a strong amount of decoherence, as you said, then you wouldn't have a signal. You wouldn't be able to recover the signal.
Okay.
So it doesn't help improve, I guess, the coherence of your signal, but it helps you verify that your signal is real. That makes sense.
Maybe I can jump in here quickly. This is Greg Benson from Monica Schleyer-Smith's group. The way that I always think about this is that the coherent basically decoherence is equivalent to tracing out part of your system, right? You're tracing out the environment, right? And if you try to take an O-talk and you trace out part of your system, you're going to lose information, right? So if you try to teleport using that and you've already traced out part of your system, you're not going to succeed. That's just another way of saying it. The operator has spread. When a system is decohered, the operator has sort of spread outside of your system S and into the environment, and so you've lost information. So that's the way I think about it.
Yeah, no, that's a very nice way of putting it. This is a minor point for the focus of our talk. So I think referring to Norman Benny's paper where they really go into detail.
Maybe I don't want to say, we shouldn't spend too much time on this, but maybe just one very quick comment. I don't understand your questioning. So, I mean, the implicative relationship, I don't know what that means. I mean, the statement, as far as we thought about it, was that, you know, Hayden Preskill was sort of, you know, a statement that in principle, there's a circuit that can recover information. And then Benny and Alexei wrote this paper that wrote down the circuit that ends up being equivalent to this traversable wormhole circuit that Bryce showed a couple slides ago. And now the question that we asked is, from the perspective of this circuit, what exactly happens when you have noise? And the statement is that because the circuit is a teleporter, in the presence of noise, you don't ever get to teleport stuff precisely because of Greg's intuition. You're sort of tracing out degrees of freedom, or your channels depolarizing you some way. So it requires this scrambling piece, and that's what allows you to distinguish. But I don't think about it as the statement that we're making here has any, says anything about Hayden Preskill. It tells me something about the protocol explicitly from Benny and Alexei. But okay, we shouldn't, maybe we can talk about it afterwards if we want to continue. Sorry, Bryce.
No problem. This is great. I mean, this is just part of the motivation that this is, you know, from an experimental perspective, has some advantage of being more verifiable or more robust in the sense that the signal, you know, is coming from the system's own dynamics and not from the external environment. The focus of our talk, though, is looking at this teleportation and its advantage for distinguishing different types of scrambling. And so here we can broadly think of two general classes of systems. So one of those classes will be systems that are holographic in nature, either they're gravity or dual theories to gravity, like SYK. And then we'll also be thinking about more generic thermalizing systems of the type that you'd find in the lab, spin chains or condensed matter. And furthermore, we'll divide these into two time scales. So we'll be looking at intermediate times, which are before the scrambling time, and late times after the scrambling time. And basically, the previous work on traversable wormholes focused on this intermediate semi-classical effect that happens in gravity and their duals. So this is the original work, and also some recent work that examined that from a microscopic perspective by this collaboration at Google X. And what we want to do here is to focus on these more generic systems. So in particular, we're going to introduce a mechanism called peak size teleportation that explains why teleportation occurs, or how teleportation occurs in generic systems at intermediate late times, and also gravity systems at late times. And doing this will allow us to reveal signatures that distinguish between these types of systems. So in particular, we'll find that these four regimes can be determined by how much information can be sent through the teleportation and the fidelity or the success of that process. Okay, so with that, let me show the circuit again and go through this in a little bit more detail. So time is running up in this circuit, and there are a few key ingredients. So one is the initial state. It'll be a highly entangled state between the left and right, and in particular this so-called thermofield double state, which is essentially a finite temperature generalization of EPR pairs. And in fact, at infinite temperature, it simply is a set of EPR pairs. There will be a unitary here, and that unitary will have some scrambling nature. And one thing to point out is that this unitary commutes with the TFD, and so it's sometimes written on the right here, or sometimes written on the left with a transpose, and those are entirely equivalent for our purposes. But just to point out, because in some of the literature, it's seen in the other way, and I'll go back and forth between those two. In the middle here, there's a coupling operator between the two sides. In some cases, this can be performed with a measurement in a classical communication, and it can also be done with entangling quantum gate. And finally, at the end, there's a local decoding acting on just a subsystem of the qubits. Okay, and so this is the circuit, and this is arisen, as Norm pointed out, in a slightly modified form in Yoshida Kataya's work, and is also the underlying circuit representation of the traversable wormholes. And from our perspective, these are all very similar, and we're going to examine the way in which they work for general systems. So when does this circuit succeed? So here's the circuit drawn in a simplified manner. And the best or most convenient way to think about this circuit is in terms of operators. So you can think of teleportation as taking an operator here on the left and moving it into an operator on the right. And teleportation succeeds when this occurs. So to measure to have teleportation, you really need two things. One, you need a strong overlap between this in state and this out state after the coupling. And this overlap is measured by this correlator here, and it's in operator language is shown down here. So we need the magnitude of this operator to be large, but importantly, we also need the phases of this operator to be aligned. What I mean by this is if you work in a complete basis of operators representing your state, you need that this correlator has the same phase for each of these operators. To illustrate this, we can look at a trivial case where we don't have any evolution or coupling. And so here we start off with an operator on the left, and we want it to be on the right. And I'll also specialize to infinite temperature. So the fundamental property of EPR pairs here is that an operator on the left can be represented as an operator on the right. And so having a high degree of overlap between these two states is actually quite trivial. But what is harder is getting the phases to align. And so here, if we think about a single qubit, we can look at the basis of operators. And what we find is that all the operators have a positive phase except for Y, because it's odd symmetric. And so here, the phases do not align. We can try to change the phases using this local decoding operation. And we'll find the convenient choice here is to apply a Y to use a Y decoding. And this flips the phases of the X and the Z operator. And so here we can align 3 out of the 4 phases. But if you ask what the fidelity of that state is, unsurprisingly, you get a trivial value. And so here we have not performed teleportation. This is just as good as choosing a random state. But what this tells us is what we need the coupling to do. So what we want the coupling to do is to flip the phase of these 3 non-identities relative to the identity. If we can do that, then we'd have unit magnitude for each of these and phase alignment. So we'd have perfect teleportation. So the operator coupling that will allow us to do this is the one introduced in the traversable wormhole papers, or it's one choice, but this will be a convenient one. And it's an operator that consists of a sum of local terms acting on the left and the right. So for instance, all the Pauli terms across some number of qubits k, which can be much smaller than the system size. Now, if you look at the effect of this operator on some initial operator, so this coupling operator on some initial operator, and we'll choose this initial operator to be a single Pauli string. What you find is that this operator measures the size of that Pauli string in terms of the number of non-identity qubits or non-identity operators on the support region. So for example, if the Pauli string here we were measuring the last 5 qubits and 4 of those are non-identity, then the eigenvalue of this operator would be the size 4. And so this is the effect in terms of operator language of this coupling. And in our circuit, we're really taking the exponential, so applying a phase that's proportional to this size. And so the way to think about the net effect is we have now some complex time-evolved operator, and we can break that up into a basis of Pauli strings. And then we can measure the distribution of sizes of those Pauli strings by the probability or the coefficient squared, and we'll get some size distribution. When you apply the operator e to the IGV, it applies a phase proportional to that size, and so the phase distribution is the same as the size distribution. And so our work will be considering cases where this distribution is tightly peaked. And so what that means is that the spread in these phases is small, such that we can approximate this distribution by a single delta function. And so what that means is that now our operator, or our coupling, just applies some overall phase to this end state. So going back to the single qubit case, we can consider now a late time evolution where we have an operator that's evolved past the scrambling time. So what this means is that an initially local operator after the scrambling time is distributed across the whole system. And so breaking it up into its poly strings, you essentially have a random set of poly strings. And these will have typical support on the entire system with some identities mixed in. So the average size will be 3/4 of the system. And because it's drawn from a binomial distribution, its variance or standard deviation will be suppressed by a factor of square root n. What this means is that you have a tightly peaked size distribution, and the coupling applies some overall phase related to the overall size. So now if we choose a coupling to be a factor of pi, to create a minus sign on each of these operators, then we can correct these phases and have this phase alignment. And so this is a way of performing teleportation, and we see that it works very generically for systems at late times and allows for a single qubit to be teleported. Now, the question is whether it can also work for multiple qubits. And so here we can perform a similar analysis and look at the different possible operators that form the basis of 2-qubit states. And here what we find is that we have now the trivial identity, we have a single non-identity operator, and we can have 2 non-identity operators. And the transpose and decoding steps actually add a different phase depending on whether you have 2 non-identity or a single non-identity. And what this means is that our coupling needs to apply a different phase depending on the initial operator. The problem at late times is that all operators evolve to be on the same order, the same size. And so what this means is that the phase applied to each of these operators will be the same, and we cannot correct each of these phases individually. So what this means is that at late times, we are not able to send multiple qubits. The single qubit case was the most that we could do. In order to send multiple qubits, what we really need is for this size to factorize. And so the size of the time evolved operator, we want it to be a sum of the sizes of the initial operators that were non-identity. And we can see this was not possible at late time, sorry, after the scrambling time. So we'll need to work at shorter time scales. To illustrate how this is possible, we can consider the case of 1D. And so here, if we have operators that are initially spread out, we generally expect them to evolve in time and grow following some light cone like this. And there are some properties of this evolution. One is that within this light cone, we expect some form of local thermalization. And so what this means is that the variance of the width of the sizes will be suppressed because of thermalization, and we have this peak size condition satisfied. We also see that if these light cones are spread out and we work at time scales such that they do not overlap, then we'll have this factorization condition such that the sizes add for the different operators. So combining these 2 factors, we expect to be able to send multiple qubits at these early time scales. We can do some numerics to verify this. So we'll be considering random unitary circuits, these block circuits like this, and we'll be simulating it with Clifford circuits. And we can scale this up to large system sizes and see, I'm plotting here now, the average size of operators, and we see that it grows linearly at short times and then saturates at some time scale once it hits the whole system. We can also plot the width of the variance of the sizes, and we see that this follows a square root law at those early time scales, note that they're on 2 different axes, so this is actually much smaller than the average size. And then at late timescales also saturates. So now if we turn on a coupling in a single qubit case, we expect that the fidelity will scale depending on the phase, depends on the phase, which is given by the coupling strength times the operator size. And because the operator size is growing linearly in time, we expect this to be a simple periodic dependence. And so indeed, if we turn on different operator coupling, we see different sinusoidal curves, and at late times, things saturate. And now, unlike in the case of late time evolution, where now if we look at multiple qubits, at late times, we cannot send multiple qubits. But if we work at these early times, we have this size addition property such that at early times, we can also have successful teleportation, as long as we work at timescales before things start to overlap. And so this is a rather trivial case, but we expect it to be very generic in these locally interacting higher dimensional systems of 1D and 2D, and given by the intuition here. We can also ask what happens in 0 dimensions. And so here things are more subtle because we don't necessarily have this spatial locality that allows us to divide up the system into different pieces. And it's also maps onto the types of systems that we expect to be holographically dual, all-to-all coupled systems like SYK. And so the question here is whether operators remain, the size distributions remain tightly peaked as it was in 0D. And so the operator size, which we're familiar with, grows exponentially because everything's talking to everything else. And so if we start off with some initial operator, it will, its growth will be exponential. And you can also ask how if you have an ensemble of different operators, how their standard deviation will evolve in time. And here, the best way to illustrate this is actually by analogy. And so if we're familiar with the case of exponential growth is similar to infectious diseases. And this is something, unfortunately, that we're seeing in lots of places right now. The standard deviation is also something that occurs in infectious diseases. And this is, if you look at 2 different places that have this infectious disease rate, but one of them has a time lag compared to the other. What it means is that the first case starts growing exponentially at an earlier time than the other. And if you look at later times, then the spread between those will also be exponential. And that's what's happening in these circuits as well, or these quantum systems, is if by chance you have a non-entangling gate to start with, then it will fall behind the rest of the systems. And if you look later on, then that kind of initial perturbation will propagate through and lead to a large distribution. So the conclusion is you don't in 0D have this suppression or this narrow size distribution if you look at local operators. But what you can do is start with a set of local operators. And so here, if you start with some number of local operators, P, which is much greater than 1, and you look at how those evolve in time, you can think about these as being uncorrelated, and so the size distribution adds. But now if you look at the fluctuations or the standard deviation among those operators, because we're taking the convolution of these independent processes, the standard deviation here will be suppressed by the factor square root P. In our circuit language, we can construct this case if instead of inserting our state directly into the unitary, we have an initial encoding step, such that we take initially local operators and blow them up to size P using some unitary encoding, and then later on decode that. So if we perform this additional encoding step, now we expect some sized peaked nature as long as we work at large P. We can also see this in numerics by running random circuits. And so here we're working with a large number of operators and also encoding with order 1,000 here. And what we see is that the sizes grow exponentially at early times before saturating. The standard deviation also grows exponentially at early times. And the difference between these is given by factor square root p. And now if we turn on a coupling, we can see that we again have successful teleportation at early times. The difference from before, of course, is that instead of being a single frequency, the frequency increases as you go along because of the exponential growth. And we also see that the fidelity decreases because the standard deviation is growing so quickly. And so in fact, once the standard deviation gets above some threshold, we have the fidelity drops to 0 because the variance in those phases is so large. We also see here that at late times, once you approach the late time thermalization, now you can return to the size, to the peak size distribution and have teleportation again. And so you may wonder whether this is unique to random circuits or whether this can actually occur in more realistic systems, time independent systems. And in fact, we actually know the answer to this already. So recently there have been some calculations on the size distribution of operators in SYK. And if you look at the results at infinite temperatures, you indeed find our prediction that the size and the variance are related by a factor of square root p. And you can also calculate the fidelity of teleportation, of the success of teleportation, which is work that was recently done by Ping Gao and Daniel Jeffress. And if you turn up, if you include a many-body operator to start, a p-body sized operator, then you find the exact same dependence that we expect. So you find this exponentially oscillating curve, and you also see that a decrease in fidelity as the size variance increases. What you don't see in these calculations is the revival at late times, and that's simply because these calculations are in the semi-classical limit and can only capture the early time effects. And so that was the story for 1 qubit. You can also ask whether this zero-dimensional channel can send multiple qubits at the same time and have this factorization or size addition property. And so here we've done some, we have some analytic argument. We've also looked at the numerics and looked at basically the maximum fidelity that occurs as you change the number of qubits. And the conclusion from this is that the channel capacity, in terms of fixing the number of coupling operators and asking how many qubits can be sent through, is linear in the number of in the size of the coupling. And this is important because it's the same scaling as was predicted in the traversable wormhole calculations, and it also matches the conventional quantum teleportation using EPR pairs. And so this represents an upper limit in terms of quantum channel capacity. And so far, and really it's the same arguments before. You work at early time such that even though you don't have spatial locality, the operators are approximately non-overlapping, and so their sizes add. And so what this means is that we've so far seen that these systems allow, these very generic systems in higher dimensions and lower dimensions, allow for teleportation, allow for the same channel capacity, scaling at least, as traversable wormholes. And so the question is, what makes these different from wormholes? And in order to see that, we actually need to go to low temperatures. And so our focus initially was on infinite temperature. If we go to low temperature, the generalization of the initial state is to take our EPR pairs and evolve them initially in imaginary time. And the key feature of this state is that it now breaks some of the entanglement that we had between the left and the right. So in particular, before we had an operator on, we could commute it to the other side or transpose it to the other side and reconstruct it in this way. Once we have a low temperature state, this is no longer the case. that it no longer commutes past this thermal density matrix. And we can measure then the degree of correlation between the two sides. And this is a quantity that can be calculated in field theoretic terms. And generically, you expect it to be less than 1 as temperature, or to be much less than 1 as you go to low temperatures. So now if we look back at our protocol, because we were applying an overall phase, we relied on this initial correlation. And so with this overall phase, or this peak size teleportation, the maximum fidelity that we can expect is given by this Whiteman function, which can be much less than 1. And this is in contrast to a gravity-based or a teleportation with a gravity model, where what has been seen is that the peak fidelity can approach an order 1 constant regardless of temperature. To illustrate this then, with our mechanism, if you go to lower temperatures, you expect the same qualitative behavior, but the magnitude has been suppressed, whereas the gravity mechanism, as you pass through a geometric wormhole, you can recover the entirety of your information. And so with that, I would like to summarize our main results. We looked at this teleportation mechanism from the perspective of operator growth, and identified this peak size mechanism that occurs at both late and intermediate times. We saw that the difference between these is in how many qubits, or the channel capacity of the system, where working at late times, only a single qubit could be sent, whereas at early times, a linear number of qubits in the number of coupling could be teleported. We also compared this peak size teleportation to gravity, and found that here the difference is not actually the channel capacity, but it's the fidelity at which information is sent, where the generic peak size mechanism is suppressed at low temperatures, but the gravity mechanism continues to hold with near perfect fidelity. There are some open questions that we're still exploring. One of them is looking into the bulk interpretation of this peak size mechanism. We know that it occurs in systems that have a large degree of stringy effect, and is also related to this notion of coherent and incoherent scrambling. This would be in incoherent scrambling systems. We're still fleshing out the details there. It's also interesting to ask whether in systems that are not purely gravitational or not purely at infinite temperature, if you go to some finite temperature, for instance, in SYK, what we've seen is that these two mechanisms can coexist. And so there's an interesting interplay that can occur, and that these boundaries are not actually sharp between these two mechanisms. Going back to the initial motivation, we think that using this protocol can provide a more robust diagnostic in both experiments and numerics for probing and identifying holographic systems. So with that, I would like to thank collaborators, Tommy Schuster, and our advisor, Norman Yao, as well as lots of discussions with these people shown here.
Thank you, Bryce.
Sure.
So we have 5 minutes for questions and discussions.
Yeah, I had a question.
Oops.
Maybe this will clarify the part of my question that I didn't understand earlier. So if you go back to your slide where you have the one-dimensional case, where you talk about where you just have some random circuit layer. Yeah, this one. So I was wondering if you guys had it seems like maybe an easy extension to consider the situation that Ehud and David Hughes and these people have been talking about, where you introduce random measurement layers interspersed in the random unitary circuit layers as like a noise model. There they care about whether or not that affects the late time entanglement structure of the state. There's some phase transition if you have a high enough measurement rate to area law late time entanglement instead of volume law late time entanglement. I guess my question here is there also some similar phase transition where above that you have non-trivial teleportation fidelity and below that you don't have non-trivial teleportation?
Yeah, it's a very good question. I'm not sure if there's a sharp phase transition in the same way. I mean, my general expectation is that any amount of noise would gradually reduce your fidelities. I don't.
Because it seems like if you have the code to implement the thing that you're already doing, implementing that seems to be not.
I don't think so. I mean, so sorry. Let me very quick comment. So I think there's two super important things, and maybe Greg can comment on this as well. The adding the measurements actually, people talk about it as if it's sort of precisely the same as thinking about noise, but it's actually very, very different. So the way, Greg said we should think about noise is in an experiment, for example, is you really trace out some knowledge about the system. So your system gets entangled with a bath, and then you really do a trace on the bath. But the really, really important thing there is that they basically keep the measurement results. So it's not exactly the same as you would think about for something that would be like coupling to an environment. On the other hand, the fact that there is this transition, you can think about it really as a scrambling transition in some sense, because once they do their protocol where they keep the measurement results and they basically measure and they sort of feedback into this protocol what those results are, then you basically go from like a volume law to an area law system, or you basically don't scramble anymore. So in that sense, I do think that if one did this protocol, that you would see something sharp actually, that it would be across this measurement rate, it would be in some deep sense, the system's no longer scrambling. Of course, I don't know how to think about this within the circuit, because I don't know how to do use star anymore. Like, it's not super clear to me what exactly, on one side, if you have some measurements, what exactly on the other side we mean by that. So maybe the two answers are: one, I don't think it's proper to think about this as coupling to an environment or decoherence. Two, if you think about it at some very high level, I think once you don't scramble anymore and you're in the area law phase, because measurements are like xenosuppressing entanglement growth, I do think you should think that you can't teleport. Implementing that in a circuit, I don't know how to do explicitly, because I don't know how to do the stars and the transposes with the measurements in a simple way.
Yeah, maybe I can also comment on this, because when we heard about this work for the first time, actually that was one of my first questions as well. And Sunwon and I thought about it a little bit. We still haven't figured it out completely, but I think so. One can think of this phase transition of measurement-induced phase transition as a transition between a state where you have a finite channel capacity still, so you're coherently transferring some qubits, and you're keeping the results of the measurement. So I think if you communicate the result of the measurement to the other system, then there is a chance that you can teleport. The problem is that instead, here you're not making one measurement, you're making an extensive number of measurements. So communicating might be a problem, because you need to post-select and communicate an exponentially large amount of information. On the other hand, if you're only, but you don't want to teleport all the qubits, you have also an extensive amount of qubits, because you have a finite channel capacity per qubit. So maybe if you want to teleport only one qubit, it's enough to not make exponentially large number of measurements. So this is something we haven't yet completely figured out, but I think using these, we can use these random unitary mappings to spin models in order to answer these questions. So we're actually working on this, and probably there is a simple classical calculation one can do to show how many measurements you need to do.
So it's possible that in order to even teleport one qubit, you needed to send this large amount of classical information.
I think so. Yeah, yeah. That's my problem. That's my worry. Yeah.
So I was wondering how crucial is like the thermal field double as a starting point for this whole protocol to work? Because it seems like it's causing you some trouble, like in the finite temperature case, and also for these experimental measurements, it's not really clear to me that that's actually what they have to start with.
Yeah, that's good. So I think for teleportation itself in an experimental setting, it's not helpful. I mean, I think that's one of our main findings is if you start off with EPR pairs, then your life is simpler. But I think from the gravity perspective, the interesting is happens that when you have a low temperature TFD state, you can overcome that lack of initial correlation. And so in some sense, the gravity evolution is kind of delocalizing your operator in such a way that it's still exploiting that initial entanglement, even though that entanglement wasn't maximal. So it's telling you something about the gravity dynamics, which is very different than what we expect based on this more naive or more generic evolution. But for practical purposes, it's not helping. And working with EPR pairs is certainly better.
Any more questions?
I have a question. So I think you made a comment that there is this auto-all case where the size distribution is not narrow.
Yeah.
Did I misunderstand? Is that the SYK model?
Yeah. So the SYK model, if you look at these large Q results, and so if you start off with a single Majorana fermion, then there is no your size distribution is not narrowly peaked. So the standard deviation of your sizes grows at the same rate as the mean.
But these results, these results we have in that paper was all for large N first. You take large N first already. Yeah. So it seems to answer your question, we should look at a finite N SYK model. And we just fix the finite N, right? Because you want to talk about that. What I just mean is that if I look at the later time, then I think it's still narrow, because
so at late times past the scrambling time, I think it is. But if you work at earlier times, then I'm not sure. I mean, our kind of generic intuition and in random unitaries, we can see this explicitly, is that things are not tightly peaked unless you start off with a many body operator to start with. And I think that that agrees with with these calculations at early times. And I'm not sure. I don't think it depends on the order of limits, but I'm not an expert.
Yeah, I agree. I think the narrow case only happened after the scrambling time.
Yeah, and so yes, exactly. And we want to contrast those two cases, because after the scrambling time, then you really have a very bounded channel capacity. But in the SYK results, you can work with a large Majorana operator, p-size operator, and then you see a similar suppression as well. And in fact, that's what Ping and Daniel found, is that for high temperatures, in order to get successful teleportation, you need to work with this large encoding. That was one of agrees with their findings.
Okay, thanks.
Okay.
I actually have a very, very quick question. So Bryce, in your last slide, or one of the last slides, you're mentioning the results in gravity. And you said that it saturates at order 1. So you mean order 1 in units of the inverse temperature? Is that what you mean, or is that different parameters?
I think it's actually, well, okay. Maybe I should clarify this a little bit. The gravity calculation diverges formally if you work in the semi-classical, no back reaction, no stringy limit. What is order 1 is if you work in SYK at low temperatures. Okay. And so this is, I guess it is beyond pure gravity, because it's regularized by some non-gravitational effects. But the point is that it's much bigger than this initial correlation, this Whiteman function, and that you can see explicitly at SYK. So that's really what I'm referring to.
So this is not
result. Yep.
Yeah. So sorry. So this is not really in the JT limit then. So when I'm doing this calculation JT gravity, this goes a little bit beyond like the phi boundary over G Newton or temperature or something like that. It's like a different parameter. Is that
yeah, it goes beyond temperature. I mean, this is in the microscopic scale. Yeah, I guess in order to see this explicitly, I mean, you know, in order, I don't know. I mean, we've been thinking in SYK, you know, the teleportation mechanism we think about is gravity, but I guess the actual magnitude of teleportation would depend on some microscopic effects. And yeah, some more generally, I mean, if you didn't have a microscopic theory, I'm not exactly sure what you can say other than, you know, it's expected to diverge well above, you know, that background or initial correlation. But good.
Sounds good. Thank you.